Hey guys, today we are going to look at k-nearest neighbor algorithm using iris dataset. I'll just assume you all know how k-nearest neighbor works and we'll directly look at the example here. So first, we need to import the package we need, and then we need to read the data. So data equals to pd.read csv iris.csv. So because our data is presented in the form of CSV, so we can use this function. And remember to save your data in the same directory of your Python file. So now we have the data, we can see the first few rows of our data. First 5 rows, data.head. So here we are. We have sepal length, sepal width, petal length, and petal width. And we want to predict the variety of the iris flower. But for simplicity, we only use petal length and petal width to predict variety. We won't use all the attributes. So let's specify this here. X is the independent attributes, is the data on the 2 columns, petal length and petal width. Okay, and the target attribute is obviously the variety. We want to predict a subspecies of a flower. So variety. Okay, here we go. Then we can visualize the data based on these 2 independent attributes. Remember, we can do the visualization because we only have 2 attributes. If we have more, we cannot visualize them on a 2D surface like your computer screen. So I'll just copy and paste some code here. Don't worry, we'll go through them later. Okay, so, oh no, wait, maybe that's better. Okay, here we go. Let me just zoom in. Okay, so the x-axis is petal length and the y-axis is petal width. And you can see the 3 subspecies here. The setosa is denoted by the red points, and versicolor is denoted by the green points, and virginica is denoted by the blue points. So if you remember, k-nearest neighbor is into classify the data like the flower into their species. So we can see the setosa is far from the other 2 groups. So we can expect the k-nearest neighbor will do fine in this subspecies since it's quite different. But you can see here, versicolor and virginica has some like this unclear region between here. So it's hard for an algorithm to tell whether a data point with this characteristic is versicolor or virginica, because there are just some of them is versicolor, some of them is virginica, but we'll see. So how do I draw this graph? We can see we need to know how many subspecies we have. So let's type it here. Species. So yeah, we have setosa, versicolor, and virginica. So we basically iterate over this array. So logically, we first draw the setosa and versicolor and virginica. And here you can see we use data.variety equals to the I index of subspecies. So it's actually an indexing help us to find the index of all the subspecies, such as for example, we want to find the indexes of setosa. So it's the first index. So it's actually a true and false. Let's see the data type. So it's a panda series of true and false. And we can use this as indexing to index our independent variables here. And then we select the petal length, so we can find our x coordinates. And similarly, we can use the same logic and find petal width, which is our y-axis. And the color, so we set up a color list here. So setosa is colored by red because it's the first first subspecies in this array. And we use label. Label is just the name of subspecies. So because we add the label here, we can just simply type plt.legend and show the legend here. And this is just the label for x-axis, label for y-axis, and a title. Okay, so this is how we draw the scatter plot. But once again, this is often not possible in the real world because you will typically have more dimension. All right, so we now have to split our data into training and testing sets. So remember, training set is used to train a k-nearest neighbor model, but testing set is used to evaluate the model performance. And you cannot use the testing set in the training phase. Otherwise, your model performance prediction or estimation will be like biased. You don't really know how your model performs. Okay, so here we go. So we specify test size equals to 0.2 means we want testing set to be 20% of total data. So this means our training set is 80% of total data. And I ran that state here just to ensure every time we run this line of code, it will give us the same result. Okay, so now we can train a k-nearest neighbor model. So it's simple. So KNN equals to k-nearest. Here. So you can actually specify the parameters. There are quite a lot. So importantly, the number of neighbors is default to be 5. And the matrix, or you can specify a lot of things actually, but the width is said to be uniform. But if you recall, we might have a tie situation where the majority votes cannot decide where the group a flower belongs to. So typically we'll just randomly assign it to any group. But we can also assign weights to like distance. Yeah, so it means across the data points will have more weights. It will affect the grouping, the classification more than the distant points. So let's say we want the n neighbors equals to 4, and we specify the weights equals to distance. Okay, then we can actually train the model. Okay, and that fit. And we have training data, and we have. So because KNN is a supervised machine learning algorithm, you have to put the label in. Okay, here we are. Then we can evaluate the model performance. So to start with, we can look at accuracy. So it's quite simple. We use the score function, and we put the independent and target variables of testing sets. So yeah, it's actually good. So 96.67% of testing sets is correctly classified. However, we might want to further investigate the model performance on separate species. So we can use classification reports. So to use classification reports, we have to predict Y first. So it's KNN model that predicts, and we put independent variables of testing sets, and we can use classification results. Here, classification report, sorry. So you have to put, let's see classification report for a second. So we have to put the true value and the predicted value in order. But actually, if the order is wrong, it's also fine. Okay. Here we are. So as we expected, Setosa is quite far from the other group, so the model performs really, really good on it. It correctly classifies all the Setosa flower. However, for versicolor and virginica, the model didn't perform perfectly on them because, as we said, there are some overlapping in this area, so the model might be confused when we have testing data in this petal length and petal width. All right, so that's pretty much it. That's how we build a KNN model and how we evaluate its performance. So thank you for watching this video and hope you enjoyed it.